Welcome back to another explainer brought to you by Forge College. If you hung out with us for our previous lesson on load balancing experiments, you probably remember that we stumbled onto some pretty fascinating performance quirks when the system was under heavy load. Well, today, we're tackling that head-on. We're going to dive deep into debugging contention and explore some advanced execution paths in Sealevel. Basically, we're rolling up our sleeves to fix those exact bottlenecks we uncovered last time.
Okay, let's dive right into this. Think of today's session as a medical diagnosis. First, we'll look at the contention bottleneck, then build our diagnostic harness, run a baseline test, apply some mitigation strategies, measure the improvements, and finally, go over your next steps.
I want you to picture something for a second. Imagine a massive 8-lane superhighway where everyone is cruising along and then suddenly all those lanes are forced to merge into one single open toll booth. Chaos, right? I mean, honking, waiting, complete and utter gridlock. Believe it or not, that is exactly what's happening inside Sealevel when we see drop transactions and skyrocketing RPC queue times. It's the exact same symptom we saw in our last load balancing lab.
Section 1. The contention bottleneck. Let's diagnose those symptoms.
So the root cause of this massive gridlock is something we call an account lock. Let's break this down into really simple terms. Imagine 200 people all desperately needing to use a single coffee shop bathroom at the exact same time. It honestly doesn't matter if the coffee shop itself is the size of an airplane hangar, that bathroom line is going to be out the door. In our system, when 200 concurrent transactions try to access and modify the exact same writable account, Sealevel is forced to process them one by one. The whole parallel processing engine just grinds to a halt.
Section 2. Building the diagnostic harness. Let's set up our lab.
To actually figure this out, we need to build a diagnostic harness, which takes 3 specific steps. First, we're going to spin up a local test validator with verbose logging turned all the way on. We need to see exactly what the runtime is doing behind the scenes. Second, we'll build and deploy a super minimal on-chain Rust program. And third, we'll configure a TypeScript test harness to aggressively fire concurrent transactions right at our program.
Now here's a really crucial tip for that second step. Your Rust program needs to do practically nothing. I'm serious, keep the on-chain compute intentionally tiny. Why? Because we're acting as surgeons here. We want to completely isolate the specific effects of account locking. If our program is doing a bunch of heavy, complex math, we might accidentally mistake a CPU compute limit for an account contention issue. So keep it super simple and highly targeted.
Section 3. Running the baseline test. Time to take our pre-op vitals.
Our baseline test is going to be incredibly aggressive. We are going to blast exactly 200 concurrent transactions per second directly at one single writable account, and we're going to sustain that intense pressure for 60 full seconds. We are deliberately creating that massive coffee shop bathroom line just to see exactly what breaks under the strain.
While this stress test is running, you need to be actively collecting 3 pieces of evidence. First, watch your RPC latencies. How long is the round trip actually taking? Second, monitor your harness success and failure rates. Are transactions timing out and dropping? And third, grab your validator logs. Save those logs and search them for the exact phrase, account already in use. Finding that phrase is literally your smoking gun. It proves contention exists and you've successfully reproduced the bottleneck.
Section 4. Applying mitigation strategies. Let's administer the treatment. Now that we've seen the chaos, let's actually write some code to change the execution path.
Our first, and frankly best, strategy is account sharding. Think back to that coffee shop analogy. Instead of having just one bathroom for 200 people, what if we built 16 of them? By tweaking our client harness to rotate its writes across 16 completely independent writable accounts, instead of hammering just one, we drastically cut down on lock collisions. Sealevel sees 16 different targets and beautifully goes right back to scheduling those transactions in parallel.
But hey, sometimes you just can't shard. If that's the case, our next mitigation is instruction splitting. If you have a massive, chunky, single transaction, there's a good chance you're holding on to that account lock for way too long. By splitting that large update into 2 or more smaller, chained sub-instructions, you effectively slash the duration of the lock for each piece. Shorter locks mean a faster turnaround and way less waiting in line for everyone else on the network.
Oh, and here's a really neat quick trick: account reordering. Simply changing the order that accounts appear in your transaction instructions can genuinely change how Sealevel groups locks for parallel execution under the hood.
So if you place your frequently read accounts earlier in the list and push your writable accounts further down, you can often significantly cut down on unavoidable serialization.
Section 5. Measuring the improvements. Let's check those post-op vitals to actually validate our optimizations.
To know if we actually fixed anything, we fill out a metric matrix. You're going to compare your baseline single hot account numbers against your numbers after sharding and after instruction splitting. You want to see these metrics drop across the board: your average RPC latency, your 90th percentile confirmation times, your failed transaction percentages, and of course, your account lock log frequency. A truly successful mitigation should give you at least a 20% reduction in your primary contention indicators.
But listen, one single good run is never enough. You need high reproducibility. When you run these tests multiple times, you want to see less than a 10% relative standard deviation in your steady-state runs. If your variance is jumping all over the place, your data is just too noisy. If that happens, you might need to adjust your transaction arrival patterns in the harness, or just increase the run duration to gather stable, trustworthy stats.
Section 6. Your next steps. Time to generate the debug report.
So, what does this all mean? The absolute most crucial takeaway here is that you must always map surface symptoms back to Sealevel's low-level execution mechanism. Stick to these 3 core principles. First, reliably reproduce the contention before you even think about optimizing. Second, pick mitigations, like sharding or splitting, that directly affect the locking model. And third, validate your success with repeatable runs and clean statistical snapshots. Your immediate next step today is to prepare your debug report artifact. Go ahead and compile your harness scripts, your log excerpts, and that metrics table showing your measured deltas. This report is going to directly link the root cause to your exact fix, and we'll be using it as our primary input for the cross-case analysis in our next lesson.
Which leaves us with one final, pretty exciting question. Are you ready to take these exact mitigations and scale them up to real-world production patterns? Because that is exactly where we're heading next. Remember, if you want to explore more courses and expand your learning on this subject, or really any other fascinating Web3 topics, be sure to head over and visit forge.college. Thanks so much for learning with me today. Keep experimenting with that code, and I will see you in the next explainer.